Exercise number 32 asks us to find the curvature of y equals the tangent of x. Now, I have an asterisk after the exercise number because I have modified this slightly. We will come back to that at the end. But for right now, let's just tackle this problem. Now, we only talk about the curvature of curves or lines, not surfaces. So we must understand this y equals tan x to exist in the xy plane, two-dimensionally. So we could represent this as a vector function. We could parameterize by x. We could say r of x is equal to the horizontal component is x. So we have like xi plus the vertical component, y, is tan x. So we have the tangent of x, j. Okay. If you don't like this, you could still parameterize by t and then just let x equal t. So you'd have r of t is equal to ti plus tangent of tj. That works out just fine. Now, if we're computing curvature, our standard go-to in most situations is theorem 10. If you take a look at theorem 10, you see that it depends on r prime and r double prime. So let's go ahead and compute those. I will write out the formula of theorem 10 in a moment, but first let's just go ahead and get our r prime and r double prime here so we have them. So r prime, derivative of x is 1, so we just have 1i plus the derivative of tangent is secant squared. And now we want r double prime. This first term is constant, so that goes to 0. The derivative of secant squared, by the chain rule we will have, well, power rule and chain rule, we have 2 times the secant of x times the derivative of secant of x, which is secant x tangent x. So cleaning that up a little bit, we have 2 secant squared x tan x times j. All right. So now we are basically ready to work out the curvature. By theorem 10, the curvature kappa of t, in this case it's x, is equal to the magnitude of the cross product of r prime with r double prime divided by the cube of the magnitude of r prime. All right. So we need the magnitude of r prime cross r double prime. So let's look at r prime is this 1i plus secant squared xj. R double prime is 2 secant squared x tan xj. The cross product, you could do this algebraically, r prime crossed with r double prime, well, j cross j is 0, so we know that's not going to contribute anything. We have the 1i cross 2 secant squared x tan x, and it's j, so I cross j is k, so we have that, right? And then we need to divide by the cube of the magnitude of r prime. And r prime is 1i plus secant squared xj. So we have that magnitude cubed. So let's start working these things out here. In the top here, we just have a single component. So the magnitude of that will be the absolute value of 2 secant squared x tan x. What I've done in this step might be obscured a little bit by the notation that's used. Remember, we have 2 different notations for magnitude in a vector calculus setting, and our textbook uses the single bar, the same as absolute value. if you were to use the other notation, remember we could use double bars to indicate those magnitudes, right? So I should write that out because it does matter that I have the K there. I was just going to say some stuff, but whatever. So we could say that the norm, or the length, or the magnitude of that vector is equal to the absolute value of the component. Started to say component, and there we go, secant squared x tan x. So if we wrote, if we use different symbols for the vector magnitude and the absolute value, it would be a little bit clearer perhaps what happened in that step. But with them being the same, it sort of disappears like that. Now we have the square root of the first component squared, which is 1, plus the second component squared. Secant squared squared is secant to the fourth. So we have that square root to the third power. That's a weird thing to write. Let me put this in parentheses for right now. Let's simplify just a little bit further. 2 is always positive, so we can safely bring that out of the absolute values. Secant squared is never negative, so we can bring that out of the absolute values. The tangent of x may be positive or negative. If we take a look back at the original statement of the problem, we were given no constraints on x, so we can't make any assumptions about that, which means that we are stuck with the absolute value there, of absolute value of tan x. Now we're dividing by this stuff. The easiest thing to do would be to turn the radical into an exponent, so we can clean that up just a little bit and say that this is 1 plus secant to the fourth x to the 3/2 power. And that would be our curvature. All right. So a couple things to note. One is that, of course, this is a scalar value, right? Curvature is scalar. We shouldn't have any vectors left. It is also non-negative. The curvature can't be negative. It's just measuring how much is it bending without really a sense of direction. Something else here is that I mentioned that I modified this exercise a bit. The original statement actually told us to use formula 11 to find the curvature of y equals tangent of x. So I modified the direction slightly, basically to illustrate how we would do this without a special case formula. Theorem 10 allows us to take the curvature of almost anything that you'll run into in this class. In the special case where the curve is in the plane and y is a function of x, you can use formula 11. And if you take a look at it, you will see that, yeah, that'll save a little bit of time. Most of the real work that we had to do, formula 11 doesn't get you around, though, right? The trickiest parts were taking the second derivative and simplifying the absolute value, working out that square root of whatever business. So, formula 11 will save you a little bit of time if you have it on hand, but at the cost of having an extra formula to worry about, right? You either need that on a reference sheet or to memorize it or whatever else. So you could certainly use formula 11. I encourage you to try that out and make sure you get the same thing, but that's mainly just take a couple of derivatives and then plug in and try to simplify what you can. We could also do this with fewer formulas and just knowing theorem 10 using the standard r prime cross r double prime over the cube of r prime, magnitudes around all those, and that will work also. Whichever approach you take, you can get the same answer.